As Derek said, I've been involved in ontology, and actually the general theme has been standards and ontology, and I became a kind of an evangelist of ontology when I came to the conclusion, which was pounded into me by colleagues, that actually ontology and semantic web technology is very well suited for the world of standards, because standards are all about precisely defining terms and relationships between terms, and the kind of standards I'm talking about are normative information standards, where we're exchanging information, and that's where I think some of this technology really can come into play as the field of standardization moves forward, getting beyond the text, natural language text renditions for standards. I think more and more computer sensible standards are the way that we're gonna move forward. So that's kind of where I'm coming from in this perspective. So I've been working a lot of years basically in the area of interoperability. And I start this talk by basically saying that if you really want to make good decisions, one thing that's often overlooked is the fact that you really need a good, seamless way of exchanging information. And a lot of people focus on new applications and great mobile apps or things like that, but they sort of give short shrift, if you like, to the interoperability issue. So I focus on that plumbing that's underneath some of the gee whiz applications that are coming out in various places. I talk about, I work in standards and then the technologies, specifically the semantic web technologies, that I think are very well suited to work hand in hand with normative information exchange standards. So this is a slide I often put up because of the glossing over that people in communications, for example, they think, oh, as soon as we have connectivity, we're good to go. And that isn't true at all. In fact, a lot of people talk about the work in communications, and at the bottom of this hourglass you can see lots of debates going on about whether you have Zigbee or Wi-Fi, IEEE, whatever standards. Those debates go on, and that's fine. That's important for those debates to go on. In the middle, actually, everyone sort of agrees that everyone's converging toward using Internet Protocol, IP, so we don't have to have a lot of battles at that level of the stack of communication standards, if you like. But then far fewer people are involved in trying to nail down agreements at the content level, if you like. And that's where I work. This is where semantic web technology works, trying to define the actual information, the meaning of the information, not just getting the bits to flow. So I try to emphasize this. I know in the US, after 9/11, there was a lot of talk about interoperability between the firemen and the police, and they really were just debating connectivity between the firemen and the police, not interoperability. They weren't trying to come to agreement on how to share map data or location data or things like that. They were really talking about talking on walkie-talkies with each other. So I want to stress that. Now, what's the big deal on the content level, the meaning layer? And this is a probably oft-repeated example that my colleagues at NASA have to suffer through, which was a classic one where they essentially sent a message to their contractors, Lockheed Martin, along the lines of, set thruster to 324.59. And what was missing there in this particular case was a trivial but important issue, which was that NASA was talking SI units and Lockheed Martin was thinking feet and pounds of thrust. So what happened is that they were missing the context for that information to go through. The number alone was not enough, and you have to provide that kind of context so that you can fully understand what information is being sent. Now, context in the good old human days depended a lot on common sense, to establish context. So the people communicating would say, oh, I know what he means, and they usually make the right inference about that. But as we go to more and more automated systems, computers, of course, are famously stupid and have terrible common sense. So we have to be much more explicit about providing context when we automate information exchange. And that's where natural language specifications and standards are lost on computers, and that would then, when an implementer reads a natural language standard, they're using their own common sense, of course, but they now may be in different contexts. The implementers I'm talking about, who are implementing systems according to a standard. So we want to move towards standards that give you more of the surrounding context, not just the core data. That can be done with information models. That's becoming increasingly popular, which is UML, the Unified Modeling Language. I intentionally skipped over XML, which a lot of people talk about, and I do that on purpose. XML really is not an information modeling language. It's an encoding specification, as John Bozak, who sort of invented XML, often says. It doesn't provide semantics. It doesn't provide that context. It's just a way of encoding or serializing information into a file format or a serial stream in a structured way, but doesn't give you that context. Now, if you go beyond UML, and this is more rare in the standards world, I wish it were more common, you can get into semantic models, ontologies sometimes called, which could be in a language such as OWL, the web ontology language, or if with a truly determined logicians out there, there is formal logic, or first order logic is the most popular for, if you like, normal life, not talking about belief systems or something like that. And that there are a number of languages such as common logic which could be used to capture first order logic statements. And these are sort of increasing levels of expressiveness and precision, but also increasing levels of difficulty, if you like, of getting your arms around them at times. So getting back to that NASA example then, what should have been sent, of course, is not just thruster setting to 324.59. They should have said this thruster setting is a measure of impulse, and the units are Newton seconds, and you can start to think about what the diagram shows here is a piece of information model or an ontology where there's a quantity kind, which is impulse, there's a quantity value, of course, the 324.59, and then there's a unit. So these things are related in well-defined ways, and this is indeed the context that is part of an even larger context of what that setting, that transmission was talking about, which would have avoided the misunderstanding and the subsequent crash of the lander. So my premise at the top here is that any API, application protocol interface, or standard basically should be supported not just by the syntax of that standard, but an information model that defines all those concepts, the relationships between those concepts, the constraints on those relationships, and those constraints on those contexts. A colleague of mine down at UC Santa Barbara said it more succinctly, basically saying, look, if we can get smart data, then you don't need such smart software. So my mission, if you like, is to endow our data with smartness, and that way you don't have to have the software having all the common sense, which we're not going to achieve in the near term, because the data is there explicitly stating all that for you. So whenever you see something like this, and I just pulled this from a colleague's sensor project here at Carnegie Mellon, where the students whip together their API specifications, which they love to do, and it basically says, okay, you're going to get this, URL with these parameters following your web call, and this is what the names of these parameters are, and they call it semantics. But I would argue, and in fact I had to reverse engineer for them, what you really want is to have a model behind there, and this information model essentially defines the vocabulary that would exist in a protocol. you know, the actual words flowing, it says, oh, these are the concepts we're talking about. We have sensors, we have a type of sensor, and every sensor has only one type. That's the one going from the box called sensor up to sensor type. This is a UML model, by the way, I'm showing on the screen here. And every sensor is housed in a device, but just a single device, okay? You can't have one sensor present in more than one device. So it starts to lay out the relationships and what makes sense and what doesn't make sense in this vocabulary of concepts. So I actually do a lot of work in the smart grid. Internet of Things is one of the many fields in which I apply this kind of technology. But in the smart electrical grid, which is a pretty active area here in the U.S., this is a part of a model which is done in UML for managing energy within a facility. And I pulled this example. This is just a part of this rather large model, because on the left-hand side, we dealt with how to handle naming things or identifying things. That's this identified object in the upper left. And every identified object, we're saying, has the possibility of having a name, but that name is of a certain type and naming authority. In other words, like currency codes, you know, as a type of name, but currency codes are controlled by somebody who controls currency code names, but some UN body or something, I'm not sure. So that's the name type authority. So you can basically say that any naming system you like, this model at least identify who is the authority that controls that naming system. So this is something that's very useful when you switch context or move between multiple contexts, because those naming authorities might be native to one group but foreign to another. So this kind of world of ontology is taking hold. There are a number of standards. I just pulled this out of a different person who works at IBM's presentation, where some of these modeled as ontologies now. A big one in the U.S. is the NIEM, the National Information Exchange Model, which came out of the justice system but is now being expanded to essentially suggested for use in all government agencies. I'm not sure if my colleague at the EPA has been exposed to NIEM at all, but it is actually, to my surprise, gaining traction quite a bit. And then there's the geolocation things. I know we have one person in the audience here from the geospatial world, and the Open Geospatial very active doing this kind of thing. Anyway, there are ontologies out there, and what's nice about semantic web technology is these things can be combined rather easily. You can mix and match and inherit one in another. So you don't have to start from ground zero when considering using an ontology for modeling your universe of discourse. Some of the concepts that pop up, and I left this in a smarter cities context because I used this slide in Dubai a few weeks back. You know, these are the concepts that come up again and again in many different domains, whether it's electricity or sensors or water. You know, you have these kinds of concepts, and we can start sort of zeroing in on common patterns, if you like, which capture the notions of location and time and organization and person. They're going to be more or less the same, and then you can specialize by adding on extra attributes if you need to in your own domain. So it works rather well in that way. So back into my smart grid world, electrical grid, this is just a partial view of the map, if you like, of the domains in smart grid itself. There's generation of electricity, there are the open markets, there's operations, there's transmission and distribution, and then there's the customers actually consuming energy in the commercial, industrial, or residential contexts. So all of these standards now are out there being developed by different groups. So the problem is not even just as simple as using an ontology to integrate a system with another system. We can use ontologies to integrate standards with other standards. And what I mean specifically is here are 4 of the standards that were on that earlier map, and all of those standards have the notion of a meter in them. And you want to hope that they are thinking the same thing when they say meter. Of course, they don't mean exactly the same thing. Some of the standards really just talk about a meter as an inventory item. You know, it just needs a serial number and you're done. You know, maybe when it was replaced and what serial number was it replaced with. Other standards talk about a meter as an active device which can be switched on, switched off, can be read. It's a sensor, obviously. And then if you look at the multi-speak meter up in the upper right-hand corner, it doesn't presume you're talking about an electrical meter. It could be a gas meter or a water meter. So that's the kind of gotcha that you can run into if you don't provide the context, because all the time you were talking electrical meter reading and someone else was thinking you were talking about a water meter reading. So that's hence the importance of context again. So what are we going to do to sort of bring some order, and how can we apply all these technology? Some, including myself in my early career, thought, well, why can't we just have one nice universal model that everyone uses, and then things will be good? And a couple of problems with that is, first of all, everyone is not living in the same context as everyone else, and they have their own vocabularies and specialized terms for very good reason. So you can't just force everyone to speak Esperanto. So I would reject that first one. I would not suggest that as a recommended course of action. But what we can do is we can have everyone live in their own universes, their own specialized domains. But if you define all your terms in what one of my colleagues calls semantic transparent way, in other words, a machine-readable form which can be inquired or queried to determine what the underlying definitions of these terms are, then you can use whatever words you like, but other systems can find out exactly what you mean by that other word, whether you mean electric meter or a water meter, by suitable inquiry. So once you have it in machine-readable form, such as using, and we're moving that way with semantic web technologies, then you open the possibility also of automatically mapping then between one world's view of the definition of terms and another. So I'm going to start speeding up just a little bit here. This is a system we've built here at Carnegie Mellon where we can take data from a wide variety of contexts. We pull it in automatically. It builds a sort of a base ontology, sort of a first cut ontology out of the terms that it encounters, in this case JSON data. And then the human, at this point still a very human step, a manual step of mapping it to what we call our base ontology, a sort of a generic ontology of concepts, allows these universes to meet one another, if you like, and find commonality. So it's an approach to allow diverse data sources to be able to share that data with each other in a common context. So this base ontology has 4 core concepts. This is, by the way, a diagrammatic form of an owl diagram. The 4 concepts are a resource, an event, a location, and a service. And these 4 core concepts, which are abstract concepts, if you like, can then be specialized to suit various specialized domains. And how we do that with our sort of our architectural framework, if you like, is you have your base ontology on the upper right there with any number of extensions for specialized domains. And when you bring in the data from the upper left there, there's JSON data with an automatic script. The manual step is providing this mapping file, if you like, which maps the incoming stuff into our generic and extended ontology. And then you push a button and it then chews on all the data according to those mappings to bring it into this neutral environment for sharing of information. So this is kind of the philosophy of this is the whole world of linked open data. Many governments and lots of other organizations are putting their data out there in OWL, or RDF triples anyway, a resource description framework, in an open way for people to inquire using a language called Sparkle. And just to illustrate, well, there's zoom in on some of that. The UK government, for example, is very active in this. Here's an example query. I don't expect it to go into great detail, but it illustrates the power of a SPARQL query in the linked open data world, where in one query I'm interrogating two different databases. One is this linked movie database, and the other one is the DBpedia, which is the linked open data version of Wikipedia, to basically answer a question which could not have been answered by either one of them, which is find me all the principal actors in any of the Star Trek movies and give me their birth dates. And the actors of the Star Trek movies is found in the movie database, and their birth dates is then cross-referenced over into the DBpedia database, and you see the results there. I ran this yesterday just to make sure it worked. And there are what it came up with. So that's a very powerful way of integrating data sources that weren't built with each other in mind in the first place. So I'm going to touch on just two more slides left. This is just the view of the kind of the messy state of Internet of Things standards these days. Everyone seems to have jumped in, and they're all fighting away on owning the turf of the Internet of Things, how to talk with each other. So I put this up with a little bit of dismay because we're going to have to wait for these battles to settle down before we know whether it's going to be the Open Industrial Internet Consortium or the Open Interconnect Consortium or whatever. So that's just we'll stay tuned on that one. And my final takeaway then is that given that we have to share information across contexts, we need to, I believe the most efficient way to do that is to explicitly define all our terms in a machine-readable way and use neutral mechanisms then to map between specialized vocabularies and terminologies and share the information through more neutral abstract models to get from A to B, if you like, and that's what that diagram is supposed to show. And that semantic web technology is particularly appropriate for this task and for the world of standards, where we can start nailing down these definitions of terms and their relationships.